Have you ever stopped and wondered what's really going on inside your computer when it adds two numbers? I mean, deep down. Well, it's not magic. It's actually a super high-speed journey on a digital highway, one that's built from pure logic. And in this explainer, we're going to build that highway, from the blueprint all the way down to the silicon.
You know, on the surface, a line of code like this looks so simple, right? But to get from that command to an actual result, well, that involves this beautifully choreographed dance between software and hardware, and it happens billions of times a second. So let's start with the blueprint for that dance. Okay, so before we can even think about building our data highway, we need the rules of the road. In the world of CPUs, that set of rules has a name, the Instruction Set Architecture, or ISA. You can think of it as the non-negotiable contract between the programmer and the processor.
The ISA is literally the language that software uses to tell the hardware what to do. It defines the whole shebang, every basic operation, from adding numbers to grabbing stuff from memory. It is the absolute lowest level a programmer can possibly see.
Think about it like this. If every single train car in a rail yard was the exact same length, managing the whole yard would be way, way simpler. It's the exact same idea here. By making every instruction a fixed length, let's say 16 bits, the CPU doesn't waste precious time trying to figure out where one instruction ends and the next one begins. This uniformity, it's a deliberate design choice that just makes everything faster and more efficient.
Now, an instruction isn't just a single block of data. It's more like a package with different compartments inside. And the layout of that package totally depends on the job it needs to do. The R format, that's for when we're working with data that's already tucked away in storage, like adding the contents of two registers. But sometimes you need to use a specific number, like right now. And that's where the I format is so clever. It actually embeds that number, the immediate value, directly inside the instruction itself.
All right, with the rules of the road firmly in place, we can finally start building our digital city and its highway system, the Datapath. This is the physical network of wires and logic gates that data actually travels through. This is the perfect analogy. Just imagine our Datapath is a massive railway switchyard. All our data moves around like little trains between different stations. You've got registers, memory, and the ALU, which is our calculator, and they all have to share one single main track called the bus. And just like a real switchyard, every single movement has to be perfectly timed and directed by the switchman, our control unit.
So let's take a quick tour of the key stations on this data highway. The program counter is kind of like our GPS, always pointing to the very next instruction. The registers, they're like these temporary holding pens, keeping data ready for action. And then you have the ALU, the arithmetic logic unit. That's the powerhouse where all the real math happens. But with all these stations sharing one single track, we run into a really fundamental problem: traffic control.
So what do you think happens? If two trains try to get on the same piece of track at the exact same moment, you're going to get a collision, a wreck. It is no different in our digital switchyard. If two different components try to shout their data onto the shared bus at the same time, we have a major, major problem.
And this isn't just some software bug you can patch later. No, this is a physical conflict. You've got two different voltages literally fighting for control of the same wire. The result? Total garbage data at best, and a fried chip at worst. This is a critical engineering problem that absolutely must be solved.
And here is the really elegant solution: a little component called a tri-state buffer. The best way to think about it is as a gate that has an off switch. Our control unit acts like a traffic cop, making sure that at any given nanosecond, only one component has the green light to talk to the bus. All the others, they're told to go into this high impedance state, which is basically like they've been electrically unplugged, making them invisible to the rest of the circuit. No collisions, no problem.
Okay, so we have our rules and we have our highway with traffic control. Now for the fun part. Let's follow one single AAD instruction on its incredible journey through the CPU, from the moment it's just a number in memory to the second it produces a result.
Every single instruction, I don't care how simple or complex it is, goes through this fundamental three-stage cycle: fetch, decode, execute. It's the constant heartbeat of the processor.
So our journey begins. The program counter, which always knows exactly where we are in the program, puts the address of our add instruction onto the main data highway. It's basically like shouting out the street address for a delivery. The RAM's own personal postal worker, the memory address register, immediately grabs that address off the bus. The RAM then looks up that location, finds our ADD instruction, and places the instruction itself back onto the bus. The package is now officially in transit.
And the package arrives. The instruction register grabs that ADD command from the bus and holds it steady. Right at this moment, the instruction is officially inside the CPU, which means the fetch phase is complete.
Now, our switchman gets to work. The control unit takes a look at the instruction, specifically a part called the opcode, and it instantly recognizes the pattern for add. It's like, aha, I know what to do, and it immediately starts flipping all the right switches to prepare the data path for an addition.
And here comes the first piece of the puzzle. The control unit gives register A the green light to place its number, let's say it's a 5, onto the data bus. That value travels straight down the highway to one of the inputs of the ALU, our CPU's calculator. So now the ALU has our first number, 5. The second number, let's say a 3, is sitting in register B, which is already connected to the ALU's other input. The control unit has already told the ALU to get ready to add, so the moment it has both numbers, bam! The calculation happens almost instantly.
And if you were to peek under the hood at the source code that defines this hardware, this is what you'd see. See? It's not magic, it's just logic. This single line of VHDL, that's a hardware description language, is the literal command that tells the silicon, hey, if the operation is add, then your output is going to be input A plus input B. Simple as that.
The final answer, in our case 8, is now ready. The ALU places this result back onto the bus. The control unit then signals our destination register, often called the accumulator, to open its gate and store that value. And just like that, the add instruction is complete.
So let's just step back for a second. What did we just witness? It wasn't just a list of steps. It was a perfectly timed sequence of events, all managed with nanosecond precision by our maestro, the control unit.
It's really like a microscopic, high-speed ballet. Every single component plays its part exactly when it's supposed to. And this incredibly intricate dance of signals and data, it happens every single time your computer does anything, from just moving your mouse across the screen to rendering a complex video.
We just watched one instruction run an entire marathon from start to finish. But what if we could run multiple instructions at the same time, kind of like a relay race? That's the whole idea behind a technique called pipelining. And trust me, it completely changes the choreography. But you know what? That's a story for another explainer. Thanks for watching.